So here we're introducing limits, okay? So before calculus, so say we have some function, all right? And this is before we have calculus. When we have this function f of x, all right? And we have some x value that we plug into the function and it creates some f of x. All that we cared about was how the function behaved at exactly x equal to 3, okay? So when we plugged in x equal to 3 here, we got some output, we got some f of 3 value. Maybe it equals, I don't know, 1 or whatever that output is, right? Who cares? But the way that we looked at it before calculus was we only cared about this one very little spot right here at x exactly equal to 3. We cared nothing about the rest of the function and how it behaved, just this one little spot right in the middle, okay? Now, after calculus, right, so we have some function, and say now that function instead is not even defined right here, right? So at x equal 3, if I plug that in, then it just gives me some indeterminate or undefined output, right? So now all of a sudden, if I have just before calculus tools, then this is completely useless to me, okay? I can't, if I try to plug in 3, it just says error, right? Maybe I'm dividing by 0 or something, who knows? And so this after calculus view is more of an eye-opening view because we care more about what's happening around the function. So if this is the calculus view, I care about what happens around the function. How does it behave around that point value instead of the before calculus view. Okay, with the before calculus view where I only cared about what happens exactly at that point. I want the after calculus view where I'm looking at all the behavior near that x equal to 3. Okay? So here, notation is key. It's probably the hardest part of calculus is getting used to all of the notation, okay? So very important that you understand the notation here, okay? So what does this say, right? This says that the limit of f of x as x approaches, see that arrow, it's approaching 3, okay? Whatever that is, all right, I think about it, I kind of think like I've got one finger, maybe my left hand index finger is running this way and my right index finger hand is running this way. And if they both meet up to one particular point, then I could say that that limit there exists, okay? So that's the idea there. The limit of a function f of x as x approaches 3. It's kind of a weird notation, but I'm telling you, this one of the hardest parts to get used to with calculus is the notation. So this is the idea of the limit here. We're approaching 3, but we're not necessarily defined at 3 itself. And remember, this is just an introduction to limits. We're going to get deeper into the math behind it. So right now it's more kind of hand waving at first so that you just get used to the idea of limits. Okay? So intuitively, all we really care about is being close to the value of x equal to 3. Okay, that's what we care about. So we're close, we're within a neighborhood of 3. Okay, so we're in the same neighborhood as 3. All right, so we are around 3, but maybe not equal to 3 itself. Okay, so that's the idea. We're close to 3. Okay, now let's do an example here. We're going to do 3 examples. So we want to approximate the given limits both numerically and graphically. So if you're asked to approximate limits numerically or graphically, this is what I'm wanting, all right? So the first problem is we're taking the limit of the function x plus 2, okay? X plus 2 is just a line with slope 1, and it's raised up 2 units from the origin, all right? And we want to know what's the limit as x plus 2 as x approaches 1, all right? So numerically with the table, how do I do this? So I'm going to set up a table. I've got a t-chart, all right? And with my t-chart, what am I going to do? Well, I'm going to have my x's on the left, and I'm going to have my y's, my function f of x on the right. And so I want values that are close to what? Close to 1, right? So what's close to 1? Well, 0.9, 0.99, 0.999, and then 1, and then 0.1001, 0.01, and 1.1, right? Those are all close values. So I'm literally going to take the value and I'm going to plug it in, okay? So how did I get 2.9 here? I literally took the 0.9 and I did what? I plugged it into this right here. I had 0.9 plus 2, and that got me the 2.9, right? So you see, I plugged it in, okay? So that's the idea. We're just plugging in things. Next, if I take 0.99 and plug it in for x here, I get 2.99. And I take 0.999 and I get 2. What does it look like this number is approaching as we get close to 1? It looks like it's getting closer and closer to a number, let's say 3, right? And that would make sense. So let's go on the other side. If I plug in 1.1 into x right here, what do I get? I get 1.1 plus 2, which is 3.1, right? That makes sense. 1.01 gets me 3.01, so it looks like I'm getting closer and closer to 3. So it's approaching 3 from this side, and it's approaching 3 from this side. Well, what would happen if I just plugged in 1? Would anything bad happen? Well, if I plug in 1 here, what do I get? I get 1 plus 2. That's not bad. That's just 3, right? So some limits are pretty easy. It literally amounts to plugging in the value of what you're taking a limit to, right? And you get 3. So that is like perfect world scenario. Everything works out great. There's no tricks. But that's not the idea of the limit, right? The limit, remember we said we cared about values that were close to it, right? So not necessarily what it was at exactly x equal to 1, but what was close to it. So these values, that's why we had to calculate these to make sure that we were actually approaching 3 on both sides with our table. Okay, so that's what we're looking for, that 3 there, that cute little face. All right, now, notation wise, what do we say? We say that the limit as x goes to 1 of the function f of x, which is x plus 2, equals 3. So the limit is of x plus 2 as x approaches 1 is 3. All right. So what if instead I wanted to do this graphically, right? So I want to do it graphically now. So how does that work graphically? Well, I'm going to graph it. So this, my friends, is f of x equals x plus 2. Remember, it's a line with slope 1, rise over run, right? And it has a y-intercept of 2. Okay? So what happens as I approach 1? Well, it looks like that function value, it actually evaluates 2, 3, okay? So here, it's actually really nice that the limit as x goes to 1 of this function is equal to the function evaluated it at that particular point. Now the question becomes, is this always going to be the case? And if it is the case always, then my gosh, that really makes our life pretty easy, right? But guess what? Life's hard, right? Life's not going to be that easy for us. So no, it is not always the case that the limit is equal to the function value, okay? So let's work a problem where this illustrates that point. So we've got the limit as x approaches 4 of the function x minus 4 divided by the square root of x minus 2. So if I tried to use the logic that I had down here, trying to make this general case, well, golly, all I got to do is plug in whatever my limit is, right? I'm limiting to 1 there, I just plug in 1. So this one, I'm limiting to 4, so I'm just going to plug in x equal to 4 and everything's going to work out. Well, guess what happens if I plug in 4 here and here? In the numerator, I get 4 minus 4, which is 0. But in the denominator, I get 2 minus 2, which is 0. So now I've got this weird situation where I've got 0 divided by 0. What in the world does that even mean, right? So that's what we call an indeterminate form, okay? So there is no value. It's indeterminate. Now, I've got to do a table. So numerically with a table, I'm going to have my x values on the left and my y values on the right, okay? So I want to plug in values that are close to 4, all right? So I pick x values that are close to 4. So 3.9, 3.99, 3.9999, right? And I play the same game on the other side of 4, okay? And we're going to see what happens whenever I plug in 3.9 into this right here for x. I get 3.9748. When I plug in 3.99, I get this, which looks like it's a little bit closer, right? It looks a little bit closer to 4. I plug in 3.999. It looks like it's almost 3.999. Man, that's pretty cool, right? Maybe. I don't know. Okay. And then let's try it from the other side. I plug in 4.1. I get 4.02248. Plug in 4.01, it's a little bit closer to 4. 4.001, that's a little bit closer and a little bit closer, right? But what happens whenever I plug in 4? I get that it does not exist. DNE is an abbreviation for does not exist, okay, guys? So if you ever see DNE, like you're going to write this a lot, so you might as well get this down. It just helps you out. If I see DNE on your paper or whatever, I know automatically that does not exist. You know, if you're like diehard and you want to write it out every time, be my guest. It's just, you know, DNE is quicker to write than does not exist, okay? So when you plug in 4, just like we said, right, it's indeterminate. It does not exist, okay? So the limit as x goes to 4 of this function is equal to 4. Now, why do we say it's equal to 4? Well, look, as I plug in numbers that are closer and closer to 4, what does it look like the value's approaching? 3.999 on one side and 4.0002 on the other. It looks like it's honing in on 4, okay? So right now, look, we're just approximating, right? We're kind of doing hand waving through tables. We're going to talk about these limit properties in a little bit in another video, okay? But using your table, you can say, based off of this information here, it looks like this going this way and going this way, we're approaching this number 4, okay? It just blows up whenever we get to the 4 itself. Now, why is this? Graphically, this is what that graph looks like. It looks like a square root curve, kind of, and it's got a hole in the graph at x equal to 4. Okay? So, this is the scenario that breaks this thesis right here that the limit is equal to just evaluating the function. If I plug in 4, I get something that's undefined, right? It does not exist. The limit does not exist, okay? However, I'm sorry. The limit exists, but the function is not a value at that point. The function is undefined at the x equal to 4. However, the limit as my function approaches 4 is 4. Okay? Sorry about that. All right. The next one here And the last example we're going to do in this video is the limit as x goes to 0 of the sine of 1 over x. Very interesting function we got going on here. All right, so with this one here, we're going to set up our table, okay? And I'm going to have values that are near 0 on both sides, okay? But whenever I plug them in, I get weird values. What do I mean by weird values? Okay, it looks like it's going down, and then all of a sudden it jumps down to negative 0.82, right? The sine function, and then if I plug in 0 here, I'm dividing by 0, which is undefined, so I can't plug in 0 there. That doesn't work, okay? On this side, it's positive 0.8269, and this side, you see here, this is just really, really kind of weird. What's going on here, right? Maybe we just need to get closer so that we can see some type of pattern. So let's get really, really close. Okay? So if I get really, really close on the positive side, what's happening? So I get close. It looks like it's getting really close to 0, but then the next order of magnitude down, it actually ends up turning negative 0.34. It's not honing in on anything. Guys, you need to remember from your pre-calculus that the sine function spits out values that are only between 1 and negative 1, okay? So the sine of whatever, doesn't matter what it is inside, is always going to spit out a number between negative 1 and a positive 1, okay? So these numbers are crazy, like they're not even honing in on something like what we had going on earlier, okay? When we looked at this earlier, even though this was falling apart here, you could still clearly see there was a pattern that it was heading towards 4 on both sides. This illustrates that it's not heading towards anything. It's almost like it's spitting out a random number every single time, okay? So what's happening graphically here? Well, it looks like as we get closer and closer to 0 from both sides, we're kind of getting into some chaos right here, okay? It just gets more and more chaotic, okay? So the limit as x goes to 0, if you think about this, 1 over a really small number happens to be a very big number. So you think about what sine is. Sine is a function that just oscillates like this no matter what, okay? So you get really big numbers. It's almost like it's spitting out some random number. So as x approaches 0, chaos breaks out, okay? We're not honing in on some specific number it's getting closer to. So graphically, you can see that the limit simply does not exist at x equal to 0, okay? So pretty interesting. Three examples that kind of give you an idea that were picked for a specific purpose, okay? And they give you an idea of things that come. One where all you literally have to do is plug in the number and voila, the limit equals what the function value would have been anyway, just like what you could have done before you ever walked into this class, right? The next one illustrating the fact that plugging in a number does not always work. When I plugged in a number, I got some indeterminate, undefined function value. It was an indeterminate limit, but through some table work, we saw that it looked like it was approaching 4, and in fact, when we looked at the graph, it clearly was approaching 4 on both sides. Okay, so maybe this is a 2, 4, 6, 8 scale, and this is 1, 2, 3, 4 scale going on here. Okay, and then this one is just what is going on. There's total chaos around the limit here. Okay, so the idea, there's three common scenarios where the limit does not exist, okay? So if I take some limit as x approaches c of some f of x, there's three ways that the limit may not exist. These are common scenarios, not necessarily every way, but the most common that you're going to run into. So number one, okay, the function f of x may approach different values on either side, okay? So what do I mean by that? Say I've got some function here, so it comes and then maybe it's there on that side, and then on this side it breaks and it goes this way. So maybe at x equal to c here, right? You see, when you're looking at it, when you're coming in on one side, it's coming to some value up there. But then when you approach it from the other side, you see that your fingers do not line up. Okay, so if I follow my fingers on both sides coming in, all right, they don't meet up whenever I get to the middle where C is. Okay, therefore you can say, okay, the limit does not exist. All right. The second scenario, a function may grow without upper or lower bound as x approaches c. So what do I mean by this? So maybe there's some, x equal to c value here, and then as I get really, really close to it, it shoots up off to infinity, right? It's going up to infinity. And then maybe on this side, it's going down to negative infinity. This is a very common graph, right? This is very common with rationals. Okay, you have horizontal and vertical asymptotes, right? We know we don't cross vertical asymptotes with polynomial functions, okay? So as you get really close to C, maybe this is your C value here, it increases without bound in the positive or the negative way, or both positive or both negative. It doesn't have to be alternating, okay? It's just some asymptote like what's going on there, okay? And then the last one, the last scenario, is the function oscillates as it approaches some specific value. And I think about this as that example that we did here. As we got really close to zero, we oscillated so much so that it just broke apart and the limit did not exist. So those are the three common ways that limits do not exist. Remember, DNE, right, does not exist. That would be a scenario where the limit does not exist. All right, guys.